when you take the derivative of a function, you lose a degree. Right? This kind of looks like a third degree polynomial that takes two terms. And the graph of a 2-degree polynomial looks like a parabola. Right? It could open up or it could open down. But the right side of a function and its derivative don't change. Okay? So if you have a parabola that's positive, the right side is going to go up. If you have a third-degree polynomial with the leading coefficient being positive, the right side is going to go up. So you can take the derivative as many times as you want. The right side will always go in the same direction, up or down, depending if that leading coefficient's positive or negative. There's the graph of the derivative of this. Any other questions from the outside? This is what we're learning in a couple days. You're graphing the derivative based off of a function, and you're graphing a function based off of the derivative. It'll take a few days to do that, maybe 3 or 2 or 3 days. Not so easy. Any other questions from this side? Good. That was quick. I recorded it.
Should I stop it?
No need to. Yes. Yeah. Close the program. What the heck is up? Driving me crazy. I can't get to. It's my assignment on 3-2.
Yeah.
So I'm just going to stick with it. Differentiability. Maybe I should not record today. It's differentiability. You guys remember how to tell if a function is continuous, right? That's when it doesn't leak water. If there's an open circle in it, the function is discontinuous. At that x value where there's an open circle in the function. Differentiability. A function must be continuous for it to be differentiable. Okay, so if you've got differentiability, just means you can take the derivative at some point. You can take the derivative of any smooth curve at any point because it has a single tangent line for any of those points. Where's my trace? Right? There's a single tangent line for any point on a smooth curve, right? The spots where you have issues is when there's a corner in a curve because it has a slope to the left of that point and has a slope to the right of that point. But if you are trying to find a single tangent, there's an infinite number of tangents when a curve has a point. It's called a corner. There's also something called a cusp, where a curve's slope to the left is negative infinity, and the slope to the right is positive infinity. Slope has a cusp, the function is not differentiable at that point. It's like, can you make a roller coaster out of the curve? If you made a roller coaster out of a smooth curve, you'd get on a roller coaster, ride it, get a lot of fun. But if you ran a roller coaster and it went like that, like all of your momentum would be going this way and all of a sudden it goes that way, you would die, right? It would not work. Could you make a rocking chair out of this as the base of the rocking chair? It would just not be comfortable, right? It's not differentiable at this point. Like you, I can't go all out in your part. Like a smooth curve is nice and smooth. Like you can make a chair out of it. You can sit on it and be so comfortable. You know, right? Be so comfortable. Like you make a chair out of this or that. That is not comfortable. That is not differentiable. Because it just wouldn't. Yeah, there. So here are points, functions that are just not differentiable. This function, the absolute value of x, is not differentiable at this corner of x equals 0. This function, y equals x to the 2/3, right, is not differentiable at this cusp at x equals 0. It's not differentiable. Right? And you can imagine making a rocking chair out of this. It'd be terrible. Right? Can you imagine trying to sit on this and use it as a swing and squeeze them in there? Just would not be comfortable. It's not differentiable. Differentiable functions are smooth. This one's a kind of a smooth function. You probably could make a roller coaster out of it. However, if a curve has a vertical tangent, remember the equation for a vertical line is x equals some number, x equals 3 or x equals 0 or x equals 5. A vertical line's slope is undefined. Right? So the derivative would also be undefined in x equals 0. A discontinuous function is not differentiable either. Right? You couldn't make a roller coaster out of it because like we don't have that. What's it called when you transport? Teleportation. We don't have that ability to do that. So until we do, not differentiable. Find all the points in the domain where f is not differentiable. Here's how to graph this absolute value function. Sure. Like a normal absolute value function. Seems like this, right? Could use the transformations to graph this specific absolute value function. Like how is this function transformed?
Right to 3.
Right to up 3. Right to up 3. So where is this function not differentiable?
2, 3.
At x equals 2. Not differentiable at x equals 2. Got it?
Is differentiable always x values, or can we do not differentiable
Always,
y
if
values?
you're telling me where it's not differentiable, the answer to where is x equals. The answer to what is y equals. What's the value of the function at? So where, they might say, what is the point of non-differentiability? That might not be a word. But the point is the location on the curve, and it's always at x equals. A point, like we will find inflection points, and we will find points of critical points, right? critical points of inflection are x equals a number, not x comma y in parentheses. Okay? So we're using the word point to not mean x comma y in parentheses. We're describing a location on a curve. Use a numerical derivative to approximate f prime of 2. You guys know what f prime of x is? Yeah?
Well,
Derivative of x cubed.
3x squared.
So
Okay.
what's the derivative of x else 2? Well, 3 times 2 squared is 12. Numerical derivative. Like, what did this say? Let's say something about numerical derivative. Yeah, we'll never do anything like that. Okay, so here is the thing. N-deriv is on your calculator. You can find derivatives of a function at points. Let's just n-deriv this right now. F of 2 is, use n-deriv with the number 12. Let me see you do that. N-deriv is under,
It's math number 8.
math number 8. So I would put,
Yeah.
I'll show you what I
D of x. How do I plug it in? Like that one.
would do. Okay, so later on when we get pretty heavy into using your calculators to do calculus, we will put the function into y equals, and then exit that screen and take the derivative and deriv 8 in terms of the variable x. So you put it in terms of the variable x, so you put an x right here. The function you're taking the derivative of, I have that in my y1. So alpha trace gives you a shortcut to y1. And if we're evaluating the derivative at a specific number, like 2, we put the number 2 there. Okay, so this is what you do in your calculator for this notation on your calculator. Press enter, you should get 12. And notice that it's a little bit off. That's because the calculator uses numbers that are approximately 2 to calculate the derivative. So the calculator will be a little bit off each time. But don't put 12.000001. That's 0.000001 off of the correct answer. So 12 is a great answer. And actually the exact correct answer. Okay, so here we have this problem. Find the absolute value function, the derivative of x equals 0. So when your y equals, you're taking out x to the third and you're going to put the absolute value of x. Absolute value of x is under math. You have to cursor over to number, num. And the first one, ABS, is the absolute value of x. So the absolute value of x, we're going to take the derivative of this function at x equals 0. So put it out of here, and we're going to math a in terms of x, alpha trace equals 0. What is the derivative of the absolute value of x at x equals 0?
0.
Not based on your calculator, but based on reality.
Undefined.
No,
Or no.
yes. Undefined is a good answer. There's no single derivative there. The calculator gives you 0, incorrect. Just so you know, the calculator can give you wrong answers.
Definition of wrong.
And in fact, the absolute value of x is not differentiable at x equals 0. Use end derivative to graph the derivative of the natural log of x. Okay, so I'm going to teach you that process. We'll use it 1,000 times when we start taking with calculator tests. Okay. So under y equals, we're going to put the natural log of x and then under y2 we're going to use end derivative. So math A. X still there. We're going to put y1 inside of the derivative, so we're taking the derivative of the first function. Y1 is, remember, alpha, let's see. Y1 you can find it under alpha trace. And here's Y1. And then, instead of putting an actual number here, x equals, we're just going to put an x there. And what that will do is calculate all the derivatives and graph it. So I'm going to go up here and highlight the natural log of x. The only thing that will be graphed will be the derivative of the natural log of x.
Natural log.
Here's the derivative of the absolute, or of the natural log of x. Do you have a guess as to what the derivative of the natural log of x is? Look, if you go to the table, if I plug in a 1, I get a 1 out. If I plug in a 2, I get a 1/2 out. If I plug in a 3, I get a 1/3 out. If I plug in 4, I get a 1/4 out. 0.25. Like, what function is that? Y equals, if I plug in a 6, I get a 1/6 out. 7, a 1/7 out. What is that function?
1
Over, yeah, 1 divided by x.
Oh.
Right? So as a function, if f of x is the natural log of x, its derivative, bless you, is 1 over x. Which is crazy. Like the slope of the tangent line for the natural log of x is always 1 over x. We graph the natural log of x. At x equals 1, the slope of the tangent line is 1. X equals 2, the slope of the tangent line is 1/2. X equals 3, the slope of the tangent line is 1/3. It's getting flatter. If a derivative